In this lecture, we study convergence of sequences in metric spaces. So, well, already we know the notion of convergence of a sequence in the set of all reals. So, let us recall. A sequence xn n belongs to set of all natural numbers of reals converges to a point x in R. So R is the set of all real numbers. If for given epsilon greater than 0, there exists a natural number n. So this natural number depends on the given epsilon. So this n equal to n epsilon, large enough natural number. This belongs to set of all naturals, such that the distance of xn from x, that is xn minus x. So this is the distance from x to xn. This is less than epsilon for all n greater than or equal to n. Okay, so this is the notion of convergence of a sequence in the set of all reals. So we use this. So we use this to define the notion of convergence of sequences in metric spaces. Okay, so before going into the definition of convergence of a sequence in a metric space, we give some definitions. For example, ball, bounded set, diameter, neighborhood. So which are essentials to study convergence of sequences in metric spaces. So let us give the definitions. Let me change the color. So let us start with considering x comma d. So let be a metric space. So here we have the definition of ball. Definition. For x naught in the metric space x and little r belongs to positive reals, the set denoted by b of x naught subscript with r, which is equal to the set of all points y in x, such that the distance between x naught and y is strictly less than r. And this is called the open ball in the metric space x comma d with center at x naught and radius r. and radius r. So pictorially, this is like following. So suppose this is metric space X, and here we have some point x naught, which is the center of the ball, and this is radius r. So the set of all points y, which has distance strictly less than r. This is ball with center at x naught and the radius r, and this is called open ball. So here look at the inequality. So the inequality is strict, and this is called open ball. And second definition, for x naught in x and r greater than 0 belongs to set of all reals, the set denoted by BR of x naught over line, this is equal to the set of all points y belongs to x, such that the distance between x naught and y, this is less or equal to r, and this is called the closed ball. So here equality is less or equal to r. Okay, this is called the closed ball in x comma d, in the metric space x comma d, with center at x naught and radius r. So this is the definition of closed ball, and so this is closed ball, and this is the definition of open ball. So here I'd like to note that if it is not mentioned by a ball, we always mean an open ball. So not if not mentioned or specified by a ball would always mean an open ball. Okay, so next we define bounded sets definition. So this is metric space X, and this is metric space X, and let's say this is some subset K. Okay, so a subset K of X is called bounded in the metric space X if there exists some ball with center at some point x naught and radius r, such that K is subset of B x naught sub r. Okay, so that is, so there exists such a ball where x naught belongs to x and r is greater than 0, some real number. Okay, so that is pictorially, if there exists a ball that that contains K. Okay, so some center x naught and radius R. So this is the definition of bounded set. And so here we have an exercise. Show that finite union of bounded sets is again bounded. That is, if let's say ki, these are I equal to 1 to n. So if these are bounded, then the union k equal to union ki over I equal to 1 to n is also bounded. Well, now we give another definition of diameter. Let K be a subset of X, then the diameter of K, then the diameter of K, and this is denoted by diam K, and this is defined by this is equal to supremum of the distance between pair of points x comma y over x comma y in K. Okay, and if this supremum is finite, okay, then we say that K has finite diameter, otherwise it has infinite diameter. Okay, so again we have an exercise. Show that a set K is bounded if and only if K has finite diameter. And second, show that the diameter of a ball, so diameter of a ball with center at some point x and a radius r, this is less or equal to 2r, and give an example. Give an example where this inequality is strict, where the inequality is strict. Okay, so next definition is of neighborhood definition. Let us label the definitions. So this is definition 1, definition 2, definition 3, this is 4. So now we defined neighborhood. So we write as neighborhood. Okay. Let X belongs to a matrix space X, then a subset omega of X is called a neighborhood of X if there exists some positive real number small enough such that the ball with center at X and radius R is contained in omega. Okay, and if this subset omega is open, if omega is open, then we call it open neighborhood of X. We say this is an open neighborhood of X, and if this is closed, then we say that omega is a closed neighborhood of X. For example, -1, 1, this is an open neighborhood of, so this open interval, so this is an open neighborhood of 0, and example 2, this closed interval -1, 1, this is a closed neighborhood of 0, and example 3, -1, 0, 0, so sorry, -1, 1, so close -1, open 1, this is a neighborhood of 0, and this is neither open nor closed. So, well, here the matrix space is R, B1. So Euclidean metric on the set of all reals. Okay, so now we are ready to define convergence of sequences in set of in matrix spaces. So now we define. So here is the definition. Let Xn, where n belongs to set of all natural numbers, be a sequence, in a matrix space X, D. So we say that the sequence Xn converges to a point, X in the matrix space x if the sequence of real numbers, that is dx comma xn. So this is the sequence of distances between x and xn. If this sequence of real numbers converges to 0, that is limit dx comma xn as n tends to infinite, this is equal to 0. And in such a case, this sequence is called, in such a case, xn and belongs to this sequence is called convergent, and that converges to x. And x is limit of the sequence, and x is called the limit of the sequence. So here, so I have written the limit of the sequence. Okay, so here we have an exercise to justify x is the limit. So exercise, show that a limit of a convergent sequence, a limit of a convergent sequence in a metric space is unique. So now we have some remark. First remark, so xn converges to a point converges to x belongs to x if for given epsilon greater than 0. So the sequence converges to a point x. So here what we have, if this sequence of real number, if this sequence of real number converges to 0, that is, if for given epsilon greater than 0, there exists some natural number large enough depending on epsilon, such that the distance between x and xn is less than epsilon for all n greater than or equal to n. And that is the sequence of real numbers. So this sequence of real number converges to 0. There's a second remark. xn, n belongs to set of all natural numbers. This sequence converges to x belongs to x if for given epsilon greater than 0, there exists n belongs to set of all naturals, and this capital N depends on a given epsilon, such that this condition holds true, and this means xn belongs to the open ball with center at x and radius epsilon, and for all n greater than or equal to n0, such that xn belongs to the open ball with center at x and radius epsilon, and this happens for all n greater than or equal to n. So third remark, this converges to this sequence converges to a point so in other words, we can say that this sequence converges to X if for given epsilon greater than 0, the sequence eventually is in the open ball. So after finitely many terms, the sequence is in this open ball. So that is the sequence belongs to set of naturals eventually in the open ball with center at X and radius epsilon. So now we give another definition. So the notion of quasi-sequence definition. So what is the so this is definition 4, this is 5. Now we give the definition 6th definition. Quasi-sequence. A sequence Xn and belongs to set of all naturals. This sequence in X comma D, the metric space X comma D is called quasi. Quasi-sequence if for given epsilon greater than 0, there exists some natural number large enough depending on epsilon such that the distance between any two points or any two terms in the sequence, so the distance between xn, xm is less than epsilon for all large enough n and m, so greater than n. So this is the definition of quasi-sequence, and so in contrast to the sequence of reals, so in real life what we have seen that every quasi-sequence is convergent. Okay, but this is not the case in metric spaces. So for example, note that, so if you consider X equal to the underlying set R minus the singleton set, let's say 0, and the metric D1 of X comma Y, this is equal to a absolute value of X minus Y for all X comma Y belongs to X. Okay, so this is underlying space and this is metric on X, so X comma D, this is metric D1, this is metric space. And if you consider the following sequence 1 over n, this is quasi. This is a quasi sequence in this metric space. In X comma D1, which is not convergent, So also in real analysis, we have seen that every bounded sequence has a subsequence which is quasi sequence, but again, this is not the case in general in the metric spaces. So example, so if you consider X equal to set of all reals with the metric D, the discrete metric, that is D of X comma Y, this is equal to 1 if X not equal to Y, and 0 if X equal to Y. This is discrete metric, and in this metric space, the sequence of natural numbers in this is bounded, which has no convergent or which has no quasi subsequence. And note that convergent sequences are quasi, but converse is not true. But converse is not true. In metric spaces. So exercise, if Xn is a quasi sequence, in metric space X comma D, then and which admits a convergent subsequence if this is quasi sequence in XD which admits a convergent subsequence, then the original sequence is also convergent. And this converges to the same limit where a convergent subsequence converges. Okay, so here we stop this lecture.